As the day gradually comes to a close, a soft golden light quietly spreads across the room, and the familiar sounds outside slowly withdraw into the distance. Perhaps you are sitting by a window or resting still after a long day, allowing your breathing to return to a steady rhythm, like water moving past an old stone along the shore. In that quiet pause, the world seems to soften, and the mind begins to open toward questions that are very small, yet very deep. Tonight, we do not hurry to find answers. Let curiosity move at its own gentle pace, like light slipping through the early morning mist. For behind familiar things, a table, the warmth of a hand, or the distant glow of the stars, lies a delicate structure that science calls quantum physics. This is not a lecture, but a quiet resting place, where ideas about reality are told slowly, so that you may listen, reflect, and gently step into the journey that is beginning. The collapse of classical physics, the end of classical certainty. There are evenings when the city gradually settles into stillness, when the distant sound of traffic fades away like a retreating tide pulling back from the shore. In such moments, it is easy to believe that this world has long been arranged in quiet stability. Bridges remain standing through seasons of rain and wind. Trains continue to cross the plains according to their appointed hours, and the stars return again and again to their familiar places in the night sky. For many centuries, this feeling belonged not only to everyday life, it was also the feeling of science. A deep reassurance that nature had been understood, that the laws guiding the universe had been written almost in full. People once watched an apple fall from a branch and realized that the same principle also held the moon within its orbit. Equations written in black ink upon white paper joined earth and sky together, turning what once seemed an immeasurable distance into a story that could be calculated. If one knew the position and velocity of an object, it was believed that its future could be predicted precisely. Much like a marble rolling across a table would arrive where the forces guiding it directed. In the light of that confidence, the world appeared orderly and dependable. Ships crossed vast oceans, guided by astronomical calculations. Factories operated according to the laws of heat and motion. Electricity began to illuminate city streets as humanity learned to describe the invisible flow of magnetic and electric fields through elegant equations. Wires stretched across continents, carrying signals like new arteries within a growing civilization. Light, too, seemed thoroughly understood. It was a wave, spreading through space like ripples across the surface of a lake after a stone had been cast into it. Patterns of brightness and darkness in interference experiments appeared with a beauty that felt almost artistic. Everything aligned with mathematics. Everything followed obediently the known laws. By the end of the 19th century, many physicists felt that the great picture was complete. There might still be small details left to refine, like brushing dust from the lens of a nearly perfect telescope. But the foundation itself no longer seemed in doubt. The universe operated like a finely crafted machine, and humanity had learned how to read its design. This confidence was not arrogance. It had been built upon centuries of patient observation. Predictions of planetary positions matched reality down to the second. Cannons fired along trajectories calculated in advance. Bridges did not collapse because engineers trusted the equations they used. The large world, the world visible to the naked eye, appeared understood. And then, small questions began to appear. not on battlefields or across the oceans, not where massive machines were at work. They emerged inside the quiet rooms of laboratories, where oil lamps or the earliest electric bulbs shone down upon instruments made of cold, polished metal. An object was heated, only a simple piece of metal placed inside a furnace. As the temperature rose, it changed color, red, then orange, then white. A familiar phenomenon, seen countless times in hearth fires or blacksmith forges. Scientists measured the light it emitted, certain that familiar equations would describe each portion of that energy precisely. At first, everything seemed correct. But when they examined regions of higher frequency light, the numbers began to slip beyond control. The equations predicted that the emitted energy would continue to rise, rising without limit. According to mathematics, a moderately warm object should have released an infinite amount of energy, as though a small candle could illuminate the entire sky. Yet in the laboratory, no explosion of light occurred. The metal continued to glow quietly, gently, and within limits. Nature showed no distress. Only the theory did. At first, it was thought to be an error. Perhaps a measuring instrument lacked sufficient precision. Perhaps some factor had been overlooked. But repeated measurements, carried out in different places by different research groups, continued to tell the same story. Equations once considered perfect now led toward infinity, where nature itself remained calm. A small crack had appeared. No one heard it break. There was no loud collapse. Only a faint sense that something deep beneath the surface was not quite right. Then light brought another question. When light shone upon the surface of metal, electrons were released. This was not surprising. Light carried energy, and energy could free particles held within matter. But what happened next resembled nothing familiar. Red light, no matter how bright, sometimes failed to free electrons from the surface. Meanwhile, blue light, even when faint, caused them to emerge immediately. Brightness did not determine the energy of each electron. Color did. It was as though light was not a continuous wave, slowly transferring energy into matter, but rather small packets, each carrying its own distinct amount of energy. There was no gradual accumulation, no waiting, either enough or not. In another corner of the laboratory, scientists observed glowing atoms. When excited, they did not emit every color continuously like a rainbow. Instead, they released distinct lines of color, sharp and separate, like individual notes within a quiet piece of music. Each atom possessed its own signature of light. Classical equations could not explain why energy chose such discrete values. 3 different questions, 3 seemingly unrelated phenomena. Yet all of them whispered the same suggestion. Perhaps energy did not flow continuously like water. Perhaps it arrived in small steps, like the ticking of a clock in a darkened room, discreet yet steady. The first solution did not arrive as a revolution. It was almost a modest compromise. A small assumption added into calculation to allow mathematical curves to match experimental results. Energy, it was proposed, could not be exchanged freely. It could appear only in specific packets. A very small change within an equation. Yet immediately, the infinities disappeared. The curves became gentle again, just as experiments had always shown. Nothing changed inside the furnace. Nothing changed in the red glow of heated metal. The world remained as quiet as before. Only the way humanity thought about it had shifted. At first, the idea resembled merely a mathematical tool, a convenient correction. No one was certain that it revealed anything profound about reality itself. But other phenomena continued to call it back, again and again, like a patient tide returning to the shore. Slowly, a gentle realization began to emerge. The laws that had built bridges, railways, and telescopes were still true. They continued to work beautifully when applied to large objects, things that could be held, seen, and measured with rulers and clocks. But when humanity looked toward a smaller world, a world too small to be seen with the eye, those laws began to fade. Not entirely wrong, simply no longer enough, like a perfect map of the ocean that could not describe each drop of water. This was not the failure of science, it was its moment of maturity. For the first time, humanity had to quietly admit something, that the universe, no matter how deeply understood, still held layers yet unopened. And in that stillness, between familiar equations and unexpected results, a new door slowly began to open. Not loudly, not in haste. Just enough for the light of a new idea to touch the room. An idea suggesting that at the smallest scales, reality might not be as smooth as once believed. That beneath the stable surface of the world existed another structure. More delicate, more discreet, and waiting to be heard with patience. Like the night sky, when one lingers a little longer in looking, the stars are still there. But their meaning has only just begun to change. The quantization of energy and light, birth of the quantum idea. And then, in the long quiet that followed those first doubts, scientists continued to observe light, not as a grand mystery, but as one might sit watching a small flame in the night, patiently waiting to see what it might reveal. Light was so familiar that in daily life it was almost invisible. It touched walls, drifted across tabletops, slipped through morning leaves, and faded as evening settled in. No one imagined that something so gentle would become the place where a profound change in humanity's understanding of reality would begin. In the quiet laboratories of early 20th century Europe, researchers continued measuring the light emitted by heated objects. Furnaces glowed a little brighter at a time, like the slow heartbeat of a sleeping creature. Numbers were recorded carefully, again and again, without haste. Familiar equations remained spread across the tables, like old companions everyone trusted. But the numbers refused to remain still. At higher frequencies, the energy predicted by theory continued to climb without limit. A mathematical path led directly toward infinity, while reality itself remained calm and finite. Heated objects did not erupt into endless sources of light. They released only a measured amount of energy and then softened. It was a strange moment. No one wished to abandon laws that had served humanity for so long. No one wished to claim that the foundation itself was wrong. And so the first solution arrived not as a rebellion, but as a cautious whisper. Max Planck, a man known for his careful nature, attempted something he himself was not entirely certain he believed. He proposed that energy was not exchanged continuously, but could only be emitted or absorbed in specific, small amounts. Not every value was allowed to exist, like steps in the dark. You cannot stand between two steps. You are either on this one or the next. Within the equation, the assumption seemed small, a new symbol, a constant added. Yet when the calculations were repeated, something unexpected happened. The infinities disappeared. The energy curve aligned perfectly with experiment, gently, as though it had always been waiting for this. No sound marked that moment. No flash of light filled the laboratory. only a page turned and a new idea quietly began to exist. At first, Planck himself regarded it as a mathematical device, a way to rescue calculations that had fallen into difficulty. Perhaps, he thought, nature was still continuous as before. Perhaps these energy packets were only a convenient description of something deeper not yet understood. But nature did not seem inclined to keep it secret for long. Elsewhere, light was tested in another way, not with furnaces, but with clean metal plates placed in darkness. When light struck them, electrons, small charged particles within the metal, were released from the surface. The phenomenon was already known. No one found it unusual that the energy of light could free particles held inside matter. But as measurements became more refined, something that did not fit began to appear. If light were a wave, as everyone believed, then a stronger wave, a brighter light, should deliver more energy to each electron. A larger wave pushes harder than a smaller one. The idea felt natural. But the electrons did not follow that intuition. When red light was made extremely bright, sometimes no electrons left the metal at all. It was as though they paid no attention to the patience of the light source trying to offer its energy. The light could grow stronger, longer, more persistent, and still, it was not enough. Meanwhile, a faint blue light caused electrons to emerge immediately. No waiting, no accumulation, no gradual change, as though each ray of light carried its own key. If the key held enough energy, the door opened at once. If not, even thousands of identical keys left the door closed. Brightness increased only the number of electrons released. But the energy of each electron depended on the color of the light. This was difficult to accept if light were only a wave. A continuous wave should have been able to transfer energy little by little, like water slowly soaking into stone. Yet nature behaved otherwise. Albert Einstein, looking at this phenomenon, proposed a bold thought. Perhaps light was not only a wave, perhaps it also behaved like small particles, not solid beads traveling through space, but discrete units of energy. Each unit carried an amount of energy determined by its color. Red light carried less energy. Blue light carried more. And each electron absorbed only one unit at a time. No sharing, no gathering together. This idea did not destroy the wave image of light. Interference patterns still existed. Light still spread and overlapped like ripples upon water. But now, behind that softness, there appeared a particle structure, as though a calm lake were composed of countless individual drops. At first, the change unsettled many people. Light had long been a symbol of continuity. It filled space without clear boundaries. To say that it also possessed a discrete nature felt like saying that the wind itself was made of invisible steps. But experiments were not concerned with human comfort. The results continued to repeat. Electrons responded only when light carried enough energy within each separate packet. Not sooner, not later. Gradually, a quiet realization spread. Perhaps energy was not a continuous flow as once imagined. Perhaps it resembled a heartbeat, each beat distinct, steady, without anything in between. From a distance, light remained a wave, soft, spreading, interfering, bending around obstacles. Yet when it touched matter, it behaved like small particles, exchanging energy one unit at a time. Two natures existing together, not excluding one another, not arguing, simply changing according to how one looked. For many, it felt like standing before the sea at night. From the distant shore, waves remain waves. But when one bends closer, Individual drops slipped through the fingers. Reality seemed to hold more layers than expected, and deep beneath the continuous surface, recognized by familiar senses, there might exist another rhythm, discreet, delicate, almost silent. The idea that energy was exchanged in small amounts began to spread into other fields. Phenomena once separate suddenly appeared connected. The sharp colored lines within atomic spectra were no longer entirely foreign mysteries. They resembled musical notes permitted to sound only at certain pitches. No notes in between, only allowed choices. And if one listened long enough, a realization both gentle and profound began to emerge. The world was not smooth like glass. It was built from small steps, small quantities, small exchanges. Not chaos, but another form of order. More discreet, like the light tonight falling through a window frame. It appears continuous, spread evenly across the floor. Yet somewhere, within a deeper layer unseen by the eye, every interaction occurs little by little, unit by unit, like quiet touches too soft to hear. And as that thought slowly settled within the minds of those who observed both sky and matter, a feeling both familiar and unfamiliar appeared, that perhaps, for the first time, humanity was touching the granular structure of reality itself, not through a loud revelation, but through patience, like the coming of night, little by little, until one realizes the world has already changed. Matter waves and the double-slit experiment, wave-particle duality. And as the thought that energy arrives in small, measured rhythms began to settle within the human mind, like the surface of a lake growing still after a passing breeze, another question quietly appeared. If light, long regarded as a gentle wave spreading through space, could behave like separate particles, then might the opposite also be true? Could the things we call matter, the tiny constituents forming a hand, a breath, and even distant stars, carry within them a softness resembling a wave? The question did not arrive as a challenge. It felt more like a reflection that comes when one looks at water in the evening and realizes that the boundary between reflection and reality can sometimes be difficult to distinguish. A young physicist, Louis de Broglie, allowed that thought to travel a little further. If light could be both wave and particle, perhaps nature did not divide the world into clear categories as humans once had. Perhaps everything possessed two aspects, depending on how it was observed. He imagined that any moving object might be accompanied by an invisible wave, not a wave in water or air, but a more delicate rhythm, inseparable from the object's own existence. At first, the idea sounded almost poetic rather than scientific. An electron so small that no one had ever directly seen it. How could it spread like ripples across a lake? Yet nature is sometimes patient with ideas that seem fragile. In later experiments, beams of electrons were directed toward thin crystals. If electrons were only small particles traveling in straight lines, one would expect them to collide and scatter at simple angles, like grains of sand thrown against a stone wall. But what appeared upon the observation screen was different. Alternating regions of brightness and darkness gradually formed, identical to the interference patterns created when light waves overlap. Gentle curves, quiet gaps, all bearing the marks of reinforcement and cancellation. Effects that occur only when waves meet waves. Electrons, charged particles once imagined as precise points in space, seemed to be behaving like waves. No one heard the moment of change. It did not shake the world beyond the laboratory. Trains continued to run. Lamps continued to glow. Yet within the stillness of repeated measurements, the boundary between matter and light began to soften. If light could be a particle, and matter could be a wave, then perhaps humanity's familiar categories were only convenient ways of thinking, not the deeper nature of reality. And so, an old experiment was seen again with new eyes. Two narrow slits were cut into a barrier. Light passed through them and formed alternating bright and dark bands upon a screen behind. A familiar result, long understood. Waves spreading through both openings overlapped. Where peaks met peaks, brightness increased. Where peaks met troughs, they canceled. A silent piece of music written in light. Now the light was replaced with electrons. If electrons were simply small particles, each one should pass through either one slit or the other. The screen should have shown only two dense regions corresponding to two separate paths. But when a stream of electrons was sent through the slits, the familiar interference pattern appeared again. Soft bands of brightness and darkness slowly emerged, as though the memory of waves remained. At first, it was thought that the electrons might be colliding with one another. Perhaps they influenced each other as they traveled. So the experiment was slowed. Electrons were released one at a time, not thousands, not hundreds, only one. Then a pause, a long quiet before the next electron was emitted. In that moment, no other electron existed within the system, no companion to interact with, nothing to disturb the journey. Each electron passed through like a solitary traveler moving down a dark corridor. On the screen behind, small points appeared. One bright mark, then another. Each impact left only a single trace, as though the electron had always been a particle. But as time passed, as thousands of marks accumulated, a familiar image slowly emerged. The points were not randomly scattered. They formed interference bands, bright and dark fringes identical to those of waves, as though each electron, somehow, had passed through both slits at once. No one saw its journey. There was no clear path connecting the moment of emission and the moment it struck the screen. Only the final result remained, and that result carried the signature of overlap. This caused no noise. No panic filled the laboratory. Only a longer silence than usual as scientists looked at the data before them. Familiar intuition began to feel insufficient. In everyday life, everything has a path. A leaf falls from a branch to the ground. A stone is thrown across a lake. With enough patience, one can trace their journeys. But here the electron seemed to refuse. It left no trace between 2 points. It appeared only when emitted and when detected. Between those moments, what occurred no longer belonged to the familiar language of trajectories or positions. Some thought that if one simply looked more closely, placing a measuring device at the slits to determine which path the electron took, the mystery would disappear. And when such a device was installed, the answer arrived, gently, yet deeply. The interference pattern vanished. The screen now showed only 2 dense regions, exactly as classical particles would produce. The electron seemed to choose a path, only one. As though the act of asking had changed the answer. No human eye needed to watch directly. Only an interaction strong enough to determine the path was required, and the interference disappeared. The softness of the wave grew quiet, giving way to the certainty of the particle. The world did not become chaotic because of this. It simply became deeper. Perhaps the electron does not carry a fixed path when no question is asked of it. Perhaps its journey is not a single straight line through space, but a spread of possibilities, like a fragrance drifting through a dark room. Only when it touches a wall does it choose where to rest. In the gentle light of those experiments, humanity began to realize that intuition shaped by large objects, stones, ships, stars seen with the naked eye, does not always apply to the very small world. Not because the small world is more chaotic, but because it is more subtle. An electron does not hesitate. It does not think. It simply follows deeper laws that humanity is slowly learning to listen to. Like waves far offshore, heard only when the city sleeps. Perhaps reality was never as simple as the straight lines drawn within imagination. Perhaps between a beginning and an ending, there has always been an open space, where many possibilities coexist, overlap, and then quietly fade when the world is required to choose. And in that quietness, as bright points continue to appear one by one upon the dark screen, a new realization slowly formed. That at its deepest level, nature does not travel along the paths familiar to us. It moves through waves of possibility, light, slow, almost without leaving footprints, like the way this night is passing beyond the window. No one sees it moving. Yet, when we look up, everything has already changed. The uncertainty principle and the wave function, probability reality. And as the small points of light continue to appear upon the dark screen of the experiment, one by one, like stars quietly emerging in the sky after sunset, a new question slowly took shape. If an electron does not travel along a single path, if between the moment it departs and the moment it is found, it carries no clearly defined position, then how can we say where it is? How can we recount its journey in the familiar way humanity has used for centuries to understand the world? In everyday life, the question seems simple. A boat drifting along a river has a position. If we look carefully enough, we know where it is, whether it moves quickly or slowly, and in which direction it travels. Error comes only from imperfect eyesight, or measuring tools not yet refined enough. We have long believed that with a perfect instrument, everything could be known precisely. That belief accompanied science for a very long time, like a reliable compass guiding a long voyage across the ocean of knowledge. But when humanity attempted to apply that idea to the electron, the compass began to tremble. To see something very small, light must be shone upon it. Light touches the object and returns to the eye or to a measuring device. At first, this seems harmless. Yet, at very small scales, light is no longer a gentle touch. Each photon carries its own energy, like a small knock upon a surface. When light is used to determine the precise position of an electron, that touch changes its motion. And when one attempts to measure its motion with great precision, its position becomes blurred. At first, this appeared to be a technical difficulty. Perhaps better tools were needed, a more refined instrument, a more careful method. But the deeper physicists looked, the clearer it became that the limitation did not disappear. It existed within the very mathematical structure used to describe that small world. Not because humanity was clumsy. This was not ignorance. It was the way reality itself is woven. At large scales, this uncertainty is so small that no one notices it. A train, a planet, or a falling leaf can still be described by clear paths. The error becomes insignificant compared with the wide distances of ordinary life. But where electrons exist, the limit cannot be ignored. There is no completely sharp position, no entirely certain velocity. Instead, something else appears, a new way of description, not through paths, but through possibility. Physicists began to speak of something that sounded strange, a kind of wave that was neither a water wave nor sound wave, but a mathematical structure spread through space. It does not declare where the electron certainly is. It only tells that if one searches, there are places where the chance of finding it is greater, and places where it is almost never found. They called it the wave function. The name resembles a real wave, yet its nature is far quieter. It is like a map of possibilities not yet realized, an invisible cloud surrounding where an electron may be found. In denser regions, the chance is greater. In thinner regions, the chance fades. The electron is not a point circling like a planet around the sun. It resembles a promise not yet fulfilled, spreading in many directions at once. Not simply A or B, but both A and B at the same time, in a way familiar imagination struggles to grasp. Like moonlight reflected upon water. It seems to exist in many places at once until a hand touches the surface and finds only a single ripple. This does not mean the electron is divided into many pieces. It means that its complete description includes many possibilities existing together. Such superposition is the natural state of the small world. Not rare, not exceptional. Simply the way things exist when they have not yet been required to choose. And measurement is no longer a passive act of observation. It becomes a meeting, an interaction strong enough that the system can no longer hold all possibilities at once. When the electron strikes the screen, it no longer spreads outward. It appears. Not because a human eye has seen it, but because it has touched the world. In that moment, one possibility becomes reality. The others quietly fade from direct experience, like paths never taken. This changes the familiar image of reality only slightly. Before, people believed the world resembled a book already written. With enough information, every future page could be read in advance. Now the book seems different. The sentences still follow strict grammar. The laws remain clear, but the next line appears only when the page is turned. Not chaos, but structured possibility. At that deeper level, reality is no longer made of objects carrying definite values at every moment. It resembles a piece of music waiting to be played. The notes are prepared, yet each sounding becomes a choice within the melody's form. This does not make the world uneasy. On the contrary, it carries a quiet gentleness. For within the limits of uncertainty, order still exists. Probabilities are not arbitrary. They repeat with such precision that experiments performed in different places on Earth continue to tell the same story, like tides rising and falling with the rhythm of the moon. Even though no one directs each individual wave. And as physicists gradually grew familiar with this new way of seeing, they realized that the world had not lost certainty. It had only changed the way certainty exists. No longer a rigid straight line, but a soft cloud of carefully arranged possibilities. At the scale of hands and breath, everything remains stable as before. Chairs still stand still. Mountains do not dissolve into mist. Yet deep beneath, every atom exists within a dance of probability, constantly shifting according to quiet laws. Perhaps that is why the night sky so often makes people feel both small and at peace. Because even when we do not know every smallest motion, the stars continue to turn, the seasons continue to return, and reality, though woven from countless possibilities, still keeps its rhythm, like this moment. You do not know exactly when the next thought will appear, yet it arrives, gently, slowly, as though the mind itself were following an invisible wave function. quietly unfolding within the stillness of night. Atomic structure and the foundation of matter, quantum structure of matter. And as the idea that reality might be woven from gentle possibilities slowly became familiar, humanity's gaze began to return to things closer at hand. Not to experiments with light or the faint traces upon dark screens, but to matter itself. The table beneath one's hand, the air passing quietly through the lungs, the dust drifting within the glow of a night lamp. If everything at the deepest level spreads like a cloud of probability, why does the world feel so steady? Why does matter not dissolve like morning mist? That question led people toward the atom. For a long time, the atom had been imagined as a miniature solar system, a heavy nucleus at the center, with electrons circling around it like planets orbiting their star. The image was elegant and easy to understand. It offered a comforting sense of familiar order. Yet when classical laws were applied carefully, something unsettling appeared. A charged particle moving in a circle must radiate energy. Like a runner circling a lake who slowly loses strength, it cannot continue forever unchanged. If electrons truly orbited the nucleus in that way, they should emit light, lose energy, and fall inward within a very short time. If that were true, every atom would collapse. No stone, no water, no living body, no stars burning in the sky. And yet, the world remains. Atoms do not vanish. They endure across billions of years. This realization did not cause panic. It felt more like a question placed gently upon a table, patiently waiting for an answer. When the wave function entered the story, the familiar image of the electron began to change. The electron was no longer a small bead circling a nucleus. It became a form of extended presence, a stable structure of probability. Instead of circular planetary paths, other shapes appeared, regions of space where the likelihood of finding the electron was greater. Some regions were round like spheres, others stretched outward like petals. Some formed more complex structures, like smoke held within an invisible shape. The electron does not run around the nucleus. It exists around it. These shapes are not arbitrary. They exist only at certain energy levels, like a string that vibrates only at notes permitted by its length and tension. When an electron occupies one of these states, it does not lose energy. It does not fall inward. It does not collapse. The atom becomes stable not because a mechanical force restrains it, but because the structure of possibility has found its own standing forms. Hydrogen, the simplest atom with one proton and one electron, became the place where this story appeared most clearly. When the equations were fully solved, discrete energy levels emerged like steps of a staircase. And when the electron moved from one step to another, light was emitted in precisely the colors astronomers had long observed in the spectra of stars. The thin colored lines in the sky were not distant mysteries after all. They were the voice of electrons changing states. Calculations written upon desks on Earth matched light arriving from stars many light years away. A quiet harmony. But electrons also carried another property, something that did not resemble motion through space. It was called spin. Spin is like an intrinsic orientation, a way an electron exists within the quantum world. When placed inside a magnetic field, it responds as though only two distinct choices are possible. Not countless directions, but two fundamental states, like two deep notes of the same instrument. This led to another realization, gentle yet far-reaching. two electrons cannot be completely identical within the same atom if all their properties match. Not because they push one another aside like people competing for space, but because the structure of the wave function does not allow it. If one attempts to place them into the same state, the mathematical description cancels itself, like two identical sounds meeting and becoming silence. And so, electrons must arrange themselves in layers. When the lowest energy level is filled, the next electron must occupy a higher one, then another higher still. Atoms have size because of this. Without such a rule, all electrons would gather close to the nucleus. Matter would shrink beyond imagination. But because they cannot share the same state, distance appears. That distance becomes the size of the atom, and the size of the atom becomes the size of the world. Different atoms, as protons are added to the nucleus, must arrange electrons in different ways. Some have outer layers nearly full, others nearly empty. Patterns repeat. The columns and rows of the periodic table emerge like a steady rhythm of breathing. Elements within the same column behave similarly because their outer electrons exist within comparable structures. Chemistry is not a separate collection of rules. It is the consequence of how electrons find their places. When two atoms come close together, something interesting happens. The electron wave function no longer belongs only to one nucleus. It spreads outward, embracing both. If this new state possesses lower energy, the system becomes more stable. A bond forms. Molecules appear. From that quiet event arise the firmness of wood, the flexibility of fabric, the fragrance of a flower, and the warmth of living skin, the size of a hand, the hardness of stone, the ability of water to flow, the color of an evening sky. All begin from how possibilities arrange themselves at the deepest level. And if one sits still long enough, it can be felt as a quiet reassurance that the world does not stand through accident. It stands because very small, very patient laws continue to unfold within every atom. Like your body at this moment. Trillions upon trillions of electrons spread around their nuclei, holding form together. None of them knows who you are. None of them thinks. Yet together they create the warmth of a chair, the rhythm of a heartbeat, and the stillness surrounding the room. An invisible architecture, gentle, precise. And as the night continues to pass, perhaps the most remarkable thing is not the strangeness of that small world, but that it has always been here, quietly, supporting everything, like the ground beneath one's feet, so easily forgotten, until one pauses and listens. Quantum field theory and forces, reality as fields. And when one sits long enough with the thought that each atom is quietly holding the world in its shape, another question begins to appear. Light as breath in the night. If everything is built from electrons spreading around nuclei, if chemical bonds are the sharing of gentle wave functions, then what truly are those electrons themselves? Are they really tiny objects, minute particles drifting through space, or only names we give, for now, to something deeper? In familiar life, we tend to think of objects as things with boundaries. A stone has a surface, a leaf has edges, a drop of water holds its own form. Even when imagining division into smaller and smaller pieces, we expect that somewhere there must exist final units, the smallest fragments of matter. Yet when physicists looked more closely, that expectation began to soften. An electron does not resemble a grain of dust waiting somewhere in space before being discovered. In the mathematical description, it appears more like a localized ripple within a wider presence. and gradually, a new idea emerged. Perhaps particles themselves are not the foundation. Perhaps the foundation is something that exists everywhere. They called it a field. A field does not sit in one place. It extends throughout space. Even where nothing seems present, the field remains, like temperature filling a room whether or not anyone notices it, or like the quiet tension stretched across the surface of a drum before it is struck. According to this view, an electron is not a small object traveling through emptiness. It is a vibration of an electron field. When the field vibrates in a certain way, an electron appears. When the vibration settles, the electron disappears. Light itself follows the same story. A photon is not a tiny bead flying through darkness. It is a ripple of the electromagnetic field moving outward. Matter and light begin to resemble waves arising upon different layers of the same ocean. This way of seeing changes something subtle. Space is no longer an empty stage upon which actors move. The stage itself becomes alive. Even in regions that seem completely empty, fields remain present, quietly capable of vibrating, and interactions between particles become conversations between fields. When two electrons repel each other, nothing solid passes between them in the familiar sense. Instead, their surrounding fields interact. At a deeper level, this can be described as tiny exchanges of energy, photons appearing and disappearing within unimaginably brief moments. No one sees them traveling like thrown balls. They are more like whispers exchanged between two regions of the same fabric. The calculations describing these processes achieve astonishing precision. Predictions agree with experiments to many decimal places, as though nature were speaking in a very clear language that humanity has only recently begun to hear. But not every interaction is the same. Within the heart of the atom, deeper transformations occur. Sometimes a neutron inside a nucleus does not remain itself. It becomes a proton, releasing an electron, along with a nearly invisible, very light particle. This process unfolds in the quiet decay of radioactive matter, within rocks deep beneath the Earth and inside aging stars. No classical mechanism allows an object to change identity in this way. But within the world of fields, such change becomes natural. Fields can exchange energy and configuration with one another. One pattern of vibration transforms into another. Heavy intermediary particles appear for the briefest moments, like temporary bridges linking two states. Through such transformations, new elements are born within stars. Slow chains of decay reshape the composition of Earth across millions of years. Deeper still, inside the atomic nucleus, there exists a force almost beyond imagination. Protons carry positive electric charge and should push each other apart. Yet they remain close together, held by a deeper bond. Within protons and neutrons are smaller entities, quarks bound by another field, powerful and enduring. The vibrations of this field, called gluons, hold them together like invisible threads that never break. No one has ever seen a quark standing alone. They always belong to a collective. Because of this, nuclei do not fall apart. Because of this, heavy elements can exist. Because of this, stone can be hard and bone can support the body. Gradually, physicists gathered familiar fields and known interactions into a unified picture. Some vibrations become matter. Others carry forces. Quarks, electrons, neutrinos, different patterns of vibration playing distinct roles within a shared symphony. Another special field also appears, spread throughout space like a thin mist. As particles move through it, they become heavier or lighter. like a person walking through deep water, feeling resistance different from walking upon dry ground. The existence of this field was confirmed only after many years of patient searching. A rare vibration within it was observed inside a vast particle accelerator. It was called the Higgs, not as a mysterious deity, simply as a sign that even mass, the feeling of heaviness or lightness in matter, may arise from interaction with an invisible background field. At an even deeper level, the equations reveal something gentle. If the laws of nature do not change with time, energy is conserved. If they do not change with position, momentum remains preserved. If they remain unchanged under rotation in space, angular motion is conserved as well. These symmetries resemble the natural balance within a song. When a melody does not depend on where it is played, its rhythm can continue without end. The fundamental forces seem to arise from deep symmetries within fields, not because someone imposed rules, but because reality's structure allows them. And when one steps back to view the whole picture, a quiet realization begins to appear. Perhaps matter is not the final foundation. The particles once imagined as the smallest bricks turn out to be temporary ripples. Beneath them are fields always present, not born, not disappearing, gently extended throughout the universe. If you place your hand upon a table now, the feeling of solidity arises because countless field vibrations are interacting, preventing electrons from passing through one another. If you look out a window, the light arriving is made of photons, oscillations of the electromagnetic field that left the sun 8 minutes ago. If you breathe in, each oxygen atom exists because strong and weak fields maintain the stability of its structure. All of this unfolds without sound, without needing to be noticed, like wind passing through a forest at night without waking anyone. Perhaps at the deepest level humanity presently understands, reality is not made of separate objects. It is an ocean of continuous fields, and everything, from light, stone, and water, to the thoughts slowly moving through your mind, is only a temporary ripple rising and settling again. Very small ripples, yet enough to create an entire world. Entanglement and information reality, non-classical connection. And if everything truly is a ripple within fields extending across space, if electrons, light, and even the solid matter beneath our hands are only temporary vibrations rising and settling again, then perhaps what matters most is not each individual ripple, but the way they relate to one another. For a wave does not carry only its own shape, it also carries the influence of other waves that have touched it before. In the quiet experiments of the past century, scientists began to notice that sometimes two quantum systems, after meeting, were no longer completely separate. They could move apart by meters, by kilometers, even farther in imagination. Yet the mathematical description of them remained a single structure. Not two stories, but a shared one. The wave function no longer belonged to each particle individually. It became a joint description of both, like two musical notes sounding from the same string. If two particles are created so that their total spin remains balanced, they do not carry fixed values from the beginning. Instead, they exist in an open state where many possibilities coexist. When one particle is measured and appears with spin oriented one way, the other immediately carries the opposite orientation. No signal travels across the distance. No message moves faster than light. It is simply a shared structure completing itself. At first, this unsettled many people. Familiar intuition suggests that every object must carry its own properties, like a suitcase already packed before departure. If two people leave a room carrying sealed cases, the contents inside have already been decided. Perhaps, it was thought, particles also carried hidden instructions, values determined at the moment they separated. But experiments became increasingly refined. Researchers changed how measurements were performed at very late moments, sometimes almost randomly. Measurements were placed so far apart that even light did not have enough time to carry information between the two locations. If particles truly possessed predetermined values, the results should have followed certain limits. But they did not. The measured correlations exceeded the boundaries allowed by any classical theory based on pre-existing properties. No thunder marked the confirmation. Only numbers repeating themselves again and again across many laboratories, as though nature were quietly whispering that separation, as we usually understand it, might not fully exist at the deepest level. Two systems that once interacted may still belong together, not through a physical thread, but through a shared structure of information. This does not allow instantaneous messaging. No one can use it to communicate faster than light. Each individual result remains random, like the toss of a coin. Yet when results are later compared, patterns appear with precision, as though two parts of the same song had always remained in harmony. This phenomenon came to be called quantum entanglement, a name that sounds complex, yet its feeling is closer to everyday life than it first appears. Like two friends who once shared a long journey. Even while living in different cities, they sometimes respond similarly to the same memory. Not because signals are exchanged, but because they once shared the same story. From this, another realization slowly emerged. The world we see each day, tables remaining still, roads not dissolving into many possibilities, does not exist because quantum behavior disappears at large scales. It remains present, only hidden. A small quantum system can preserve superposition for a long time if carefully isolated. But in ordinary life, everything constantly interacts with its surroundings. Light, heat, air, vibration. Countless small touches occur every second. Each interaction resembles a conversation, and when a quantum system speaks with too many things at once, its superposition spreads into the surrounding environment. Information disperses. Different possibilities no longer interfere clearly. This process is called decoherence, not a sudden collapse, but a gradual dilution, like a drop of ink falling into water. At first distinct, then spreading, then impossible to gather again. Because of this, the large world becomes stable. A chair does not exist in two places at once. It's because countless interactions with the environment remove observable interference between different possibilities. Classical reality appears not because quantum theory is wrong, but because quantum behavior is too rich. When interactions become numerous enough, only a single clear image remains for the observer. In the light of that realization, something else began to change. Information, once thought to be merely symbols on paper or electrical signals in wires, turned out to be physical. No information exists without being carried by a material system. And if matter obeys quantum laws, then information does as well. In the familiar world, a bit of information is a choice between two states: yes or no, 1 or 0. But a quantum system can exist in a superposition of both, not half of each, but both together within a defined structure. Such a unit is called a qubit. Before measurement, it is not simply an answer. It is an open possibility. Many qubits can become entangled with one another. When this happens, the state of the whole system can no longer be separated into independent parts. Like a chord that cannot be divided into individual notes without losing its sound. Scientists began to realize that interference and entanglement, once sources of confusion in fundamental experiments, could become tools. If a quantum system is controlled with sufficient delicacy, possibilities can overlap in ways that strengthen correct answers and fade incorrect ones. Not because a quantum computer magically tries every possibility at once, but because possibilities interfere like waves upon water. The earliest models appeared very small, fragile, easily disturbed by the environment. A single thermal vibration or a wandering photon could dissolve a superposition. Yet even so, early experiments revealed something new. Information is not merely something stored. It can be a physical resource. Entanglement becomes connection. Superposition becomes capacity. Interference becomes a method of computation. Somewhere along the way, physics began to touch philosophy, not through argument, but through gentle questioning. If two systems that once interacted can never be entirely separate, if information about them exists within relationships rather than within isolated parts, then perhaps the world is not a collection of independent objects. Perhaps it resembles a vast woven fabric. Each thread gains meaning through the way it intertwines with others. Even now, as you listen, countless photons from a screen or a lamp are touching your eyes. Atoms within your body are exchanging energy with the surrounding air. There are no completely sealed boundaries, only different degrees of connection. And at the deepest level humanity has glimpsed, information does not stand outside nature. It is part of nature, following the same laws as light and matter, gentle, precise, at times stranger than intuition, yet far kinder than the fears that first accompanied it. For in a universe where everything may become entangled in subtle ways, perhaps nothing is ever entirely alone. Even the thoughts moving through your mind at this moment are small ripples within a far greater network. A network still quietly unfolding as the night continues to deepen. Quantum technology and macroscopic quantum effects. And as the thought that information itself follows quantum laws gradually becomes familiar, something else begins to appear, quietly and without urgency. Concepts that once lived only inside laboratories, superposition, entanglement, the wave function, did not remain confined to equations or to carefully shielded instruments hidden in the basements of research institutes. They left those places long ago, stepping into ordinary life in ways we sometimes do not notice. If one sits still for a moment and listens to the room around them, traces of these ideas can be found almost everywhere. There are materials which, when cooled until thermal motion nearly fades away, become entirely different. Electric current moves through them without resistance, without heating, without losing energy. Electrons no longer collide chaotically like pedestrians pressing through a crowded street. They begin to move together as though becoming a shared presence, a collective rhythm spreading throughout the material. This phenomenon is called superconductivity, yet felt rather than defined by terminology. It resembles a choir finding perfect harmony. When every voice aligns, individual collisions disappear. Only a continuous flow remains. Because of this, magnetic fields can be pushed out of the material. Trains can float above their tracks. Medical scanners can look deep within the body without opening a wound. A quantum state once fragile within small experiments, has extended itself to a scale that a hand can touch. Light tells a similar story. Most light around us comes from countless atoms emitting independently. Each atom resembles a person speaking alone, producing a mixture of sound that feels scattered and uncoordinated. But under certain special conditions, light can become synchronized. A photon passes through an excited atom, and that atom releases a second photon identical to the first. The same energy, the same direction, the same rhythm. Mirrors placed facing one another allow these photons to pass back and forth repeatedly, like a whisper echoed along a long corridor. Gradually, the light becomes unified. A narrow, stable, nearly perfect beam appears. The laser. Today it exists in surgical rooms, within cables carrying data across oceans, and in instruments measuring the distance to the moon. Yet behind its familiarity lies a gentle idea. Photons can share the same state. Not disorder, but quantum order extended outward. Time itself is kept in a similar way. Somewhere on Earth, atoms are held within extraordinarily stable conditions. Their electrons move between energy levels with frequencies so precise they scarcely change. Each transition becomes a small heartbeat of nature. Atomic clocks listen to that rhythm. They are so accurate that they may lose less than a single second across millions of years. Because of this, positioning systems know where you stand, even within a few meters, upon a planet spinning thousands of kilometers each hour. Even the idea of security, something that once seemed closer to society than to physics, begins to change when quantum principles enter the story. If two particles of light become entangled, anyone attempting to secretly measure them leaves a trace. The act of interference alters the state. Observation cannot occur without contact. New communication systems make use of this, not because an eavesdropper lacks computational power, but because nature itself does not permit silent listening. If someone tries to listen, you will know. A form of security grounded not in promise, but in physical law. Elsewhere, researchers prepare atoms or photons in states of extraordinary sensitivity. Even a small change in magnetic fields or gravity is enough to disturb them. From this arise quantum sensors. They can detect subtle variations beneath the Earth's surface, helping locate water or mineral resources. They can measure the slight slowing of time in stronger gravitational fields, testing deep predictions of relativity. Ideas that once sounded philosophical become instruments, not because the world has changed, but because humanity has learned how to listen to laws that were always present. Gradually, a new field has formed, a place where engineers and physicists work together with delicate states of matter. They build machines guided not only by electric currents or mechanical gears, but by superposition and entanglement. It is not always easy. A small thermal vibration, a wandering photon, or a trace of electronic noise can destroy a quantum state. It resembles trying to keep a lake perfectly still in the presence of a gentle wind. Yet, step by step, they learn to shield, to cool, and to create quiet enough spaces for such phenomena to last longer. Quantum engineering does not attempt to force nature. It resembles preparing a quiet room where very small voices may finally be heard. And when one looks back, what feels most remarkable is not the strangeness of these technologies, but their familiarity. You may already be using laser light without thinking about it. You may already be guided by atomic clocks when opening a map on a phone. Medical devices, communication systems, sensitive sensors. All rest upon laws that once puzzled humanity when they were first observed. Quantum theory was never only a story of laboratories. It has always been here, in the current moving through a wire, in the light reflected from a window, in the signal quietly traveling through space to carry this sound, like breathing. We rarely think about it, yet it remains there, steady, supporting every moment. And when this becomes clear, the distance between distant equations and the quiet room around us seems to dissolve. The universe is not only understood through quantum ideas, it is being built each day by those same gentle laws. And when one begins to realize that the smallest laws have quietly entered everyday life, slipping through the light within a room, through the steady pulse of clocks, and through silent signals crossing the sky to guide humanity, another feeling slowly emerges. Not the end of a journey of understanding, but something like walking a long distance through the night and suddenly seeing the horizon widen. For even though quantum equations have predicted countless experiments with remarkable accuracy, even though they allow the construction of delicate and reliable technologies, a very quiet question remains. The numbers work, but what do they say about reality? When an electron exists as a cloud of possibility before it is measured, what does that truly mean? Does it genuinely spread through space, or is that only the way humans describe what can be known? Some choose a very simple view. For them, the wave function does not need to be a physical object. It resembles a notebook, a tool for predicting probabilities. When a measurement occurs, information changes, not because the world mysteriously transforms, but because our knowledge has been updated. In that view, nature remains as calm as before. Science does not need to tell a story about what really happens when no one looks. It needs only to describe what will be observed when a question is asked. Others feel differently. If the equations always evolve continuously, if nothing within them clearly shows that the wave function truly stops, then perhaps all possibilities continue to exist. Each measurement outcome does not erase the alternatives, but separates experience into different branches. Somewhere in that imagination, every outcome occurs, not as a strange tale of science fiction, but like a forest where every path continues forward, even though the traveler experiences only one. No one can see the other branches. No experiment so far clearly distinguishes between these interpretations. The equations give the same results, as though nature is content to leave a small space open for reflection. Even the moment of measurement, when possibility becomes event, still carries an unfinished question. Interaction with the environment explains why the large world becomes stable, why a table does not exist in many places at once. Yet what determines the specific result in each individual instance continues to be spoken of with humility, like the fading of daylight into night. We know it happens, yet the exact moment when twilight ends is difficult to name. In another direction, an even greater distance remains to be crossed. Quantum theory describes fields and particles with extraordinary precision. Gravity, the curvature of space and time, speaks another language. Einstein's equations trace the motion of planets, the formation of black holes, and the expansion of the universe. Each theory succeeds within its own territory. But when they are placed within the same story, especially in extreme places such as the first moments of the universe or deep within a black hole, the equations begin to disagree. Infinities appear again, like the small cracks that opened at the beginning of the previous century. Some imagine that space and time themselves may not be continuous, but woven from smaller units. Others speak of vibrating strings instead of point-like particles. Yet for now, nature remains silent. On cosmic scales, another mystery quietly waits. Galaxies rotate faster than visible matter alone can hold together. Something unseen seems to add extra gravity. It is called dark matter. It does not shine. It does not reflect. It leaves only traces through the motion of stars. Farther still, the expansion of the universe is accelerating, as though space itself is gently pushing outward. An energy of unknown origin seems to fill the emptiness. Dark energy. Two names given to two things not yet understood. Together, they make up most of the universe. Yet neither has been directly touched. This does not diminish what has already been learned. It simply widens the horizon. For science has never been a journey toward a final answer. It resembles walking into the sea at dawn. With each step forward, the shoreline behind becomes clearer. Yet the ocean ahead grows wider. Quantum theory has allowed humanity to understand why atoms remain stable, why chemistry exists, why light travels, and why modern technology can function. Its predictions are astonishingly precise, yet its deeper meaning, what reality is when no one observes, remains open. Perhaps this is not failure, but a gentle reminder that understanding always walks beside humility. Even now, as you sit within a quiet room, quantum fields continue to fluctuate around you. Photons from distant sources touch your eyes. Atoms within your body exchange energy with the surrounding air. An ordered universe continues to unfold. And within that order, questions remain unanswered. Not an empty space to fear, but a space in which to continue walking. Like the night sky, you may recognize familiar constellations, know their paths, understand how long their light has traveled. Yet, between the stars, vast darkness remains. It is that darkness that gives the sky its depth. And perhaps it is the unknown itself, quiet and patient, where the journey of human curiosity always begins again. Like the next breath, arriving, very gently,